my screen. Okay, so apparently the host is disabling screen sharing.
You should be able to do it now. I always forget to turn it on in the beginning of every session.
All right, we'll try again. That looks more promising.
Do you just need to go to the presentation mode?
Yeah, I'm just doing that now.
Okay.
How does that look?
You have the view of the speaker. Click on the settings and swap presenter.
Does that work?
That's perfect.
Great. This has happened before. Okay, well, good morning, everybody. So as Amarina was saying, I'm Paul McKeever. I'm the head of electrical research at Catapult. So just to give you a bit more background on myself, I've actually worked in the offshore renewable sector for about 15 years. And then prior to that, I worked in the automotive sector, and I also worked in the railway sector as well. So 3 different sectors with different challenges, but certainly an interesting benchmarking exercise when I get time to reflect on what I've done over the last number of years. So what I'm going to try and do today is give you an overview of how the electrical systems in the offshore wind sector have changed maybe in the last 20 years or so. I'm covering quite a lot of ground because it's electrical systems. So later today, you're going to have presentations on dynamic cables in particular. I know Francesco, who follows me, is going to be focusing on dynamic cables. So obviously, my subject area is much broader. So I'm not going to go into a huge amount of detail in any particular area, but I'm trying to give you sort of the bigger picture view of how electrical systems in our sector have evolved. Okay, so moving on to the next slide. So first of all, I'm going to give you, I guess, a kind of an anecdote, a UK anecdote of offshore wind in the UK in the early days. Interesting example. And then I'm going to split the electrical system development into certain areas. So I've got a little bit on how the powertrain technologies have changed in that kind of time period. I'm going to cover some of the cable and transmission technologies that have been considered or changed or are being considered. I've got a section on smarter wind turbines where I can explain how the role of the wind turbine is changing as the wider energy system is evolving. Floating wind, which I'm sure a number of you are aware of, is becoming more and more important for the offshore wind sector. So there's some areas covered there. And then I also want to talk about how wind is playing its part in the evolution of the energy system. And then to sort of conclude the presentation, I've got a couple of examples of maybe some things that might happen in the future. Okay, so something of interest there too. What I've done with this presentation, I've focused on technical or techno-economic changes or considerations. I've not really gone into market or regulatory aspects. There is a lot of research in that area as well, but we just haven't got enough time. You know, I could spend just as long talking to you about market and regulatory challenges, or at least somebody could be doing that. So I've focused today on the technical and maybe some of the economic points. Okay, so offshore wind, the early days. So what I've got here is I've got some photographs of the Blythe offshore wind farm, which doesn't actually exist anymore. But the reason why I've picked this is, well, 2 reasons. One, because it's very, very close to where the Catapult offices are in Blythe. So when it was there, we used to be able to see this from the offices. And secondly, it was the UK's first offshore wind farm. So it was commissioned in December 2000, and it was classed as an offshore wind farm because there was 2 turbines. It wasn't just a single turbine. So you're starting hopefully to get a picture of the scale of things in the year 2000. There had previously been some earlier offshore wind farm developments in the 1990s, particularly in sort of Danish waters, but this was the first one in the UK. So the consortium there, as you can see, included a number of industry partners that may be familiar, and it was decommissioned in 2019. So the 2 turbines that were on the UK wind farm, they were Vestas 2 megawatt V66 turbines. They weren't actually offshore turbines, they were onshore turbines that were adapted for offshore. They were the largest ones at the time and fairly close to shore, as you can see, 1.6 kilometers, fairly shallow water, sort of circa 10 meters, and it was a 33 kV connection to the electrical grid. So what could go wrong? So the first thing I wanted to point out was the project, it was partly reliant on public funding. So there was an EU framework funding element to the project. So the consortium wasn't exactly awash with cash, or they weren't prepared to put lots and lots of money into the project. And this kind of manifested itself in some of the challenges and problems that occurred during the life of the turbines. So firstly, I'm assuming due to funding limitations, the cables themselves, the cables to shore, were not clamped to the seabed, which was in that part of the North Sea is very rocky. So probably not totally unexpectedly, the cables failed over time. So firstly, the cable between the 2 turbines failed, which meant that one of them was out of operation, and that was eventually repaired. And then the cable to shore failed, which meant both turbines were out of operation. The second point I wanted to make was the turbines were not designed for offshore, as I mentioned previously. So they were subjected to a saline and contaminated environment in terms of, you know, sand and dust that they weren't potentially experiencing onshore, and corrosion was therefore a significant consideration, an issue. And I understand that when the turbines were decommissioned, they weren't exactly in the best of state inside the nacelles. And a question that I don't know the answer to, but it does make me think, and maybe others think as well, is in those 19 years, how many operating hours did those turbines actually do, given the problems that I've explained above? Certainly, as I used to drive to work and drive home from work on a daily basis, I remember seeing the turbines often not moving in that time period. So I've worked in Blythe since 2006. So I saw most of that lifetime of those 2 turbines. So not exactly a great start for offshore wind. And related to that, there was an IEE Review magazine article around that time in the early 2000s. So IEE is now, of course, the IET. And they were asking questions at the time, such as, will UK offshore wind ever be realised? Is the environment too challenging? Why aren't we focusing on onshore wind versus offshore wind? So it's interesting that that was only 20 years ago, probably less than 20 years ago. And I think if we asked those questions again today, we would get very different responses. So probably not the greatest of starts for offshore wind, but this is how technology tends to be. It's quite hard at the start, but if you persevere and you invest in it, then you can get very different results. And if you look at where offshore wind is today in 2021, we're in a very different place. So much more positive. So now I'm going to move on to some of the powertrain technologies. So quickly explaining defig, so doubly fed induction generators. So this topology was used in a lot of the early wind turbines. And as you can see from the diagram on the left, the converter itself isn't fully rated. So it's connected to the generator, but it's not a fully rated converter. And the advantage of this was it was quite simple and low cost, but the biggest drawback was there are control limitations to it, particularly around voltage control and overall wind turbine control. So as the turbines get bigger and bigger, and you know, this defig, we were talking about kilowatt machines at the time, or maybe into the sort of early megawatt range. But now, of course, in offshore wind, we're talking about 10 megawatt, 15 megawatt, 20 megawatt plus kind of range. So this topology isn't really suitable for that kind of size. So of course, a few years ago, maybe about 10, 15 years ago, the industry started looking more at geared solutions as the turbines got bigger. So you can see here from the diagram, we've got a gearbox and a generator, and we've got a fully rated converter. So this afforded better control. But one of the challenges, particularly with the early offshore wind turbines using this drivetrain or powertrain topology, was reliability. And there were some issues, particularly with gearboxes and converters. There was an interesting FP7 project, I think completed about 10 years ago, called ReliaWind, which gave some useful insights into this kind of challenge. And that's maybe one of the reasons why the industry started to consider direct drive powertrains more and more. So direct drive, it still maintains the fully rated converter, but now you've effectively removed the gearbox. So you're now dependent on a very large generator, and that has a very slow rotational speed. So it does mean that you know, large rotational speed, the generator challenges are different, but the turbines are much bigger. So there are certain opportunities that are afforded in terms of where you put the equipment. And that's essentially what the comment on the left-hand side of the slide says. So in terms of the converter and the transformer, you don't necessarily have to have those in the nacelle of the wind turbine, and in many cases are actually located in the tower or close to the foundation of the turbine. So now I'm going to move on to cable and transmission technology. So what I've put up here is this is effectively the new Blythe wind farm. This isn't the original one, the original 2 turbines one. This is the current demonstration wind farm that was that's managed by EDF Renewables. So at the moment, there are 5 turbines operating on that site, 8.3 megawatt turbines. There's the possibility to increase that to up to 15, 100 megawatt grid connection, but it's currently 5. And the reason why I've put this up as an example is a demonstrator project such as this is really useful. It's really useful for helping us accelerate technology shifts in the industry. And one of the things that was done on this project when those 5 turbines were installed, everybody thinks about the foundations. So you can see on the picture on the right-hand side, it's a gravity-based foundation. So these foundations were actually built in a shipyard close to the site. They were towed out, and then they were basically flooded with sand and water and then submerged into position. So quite a novel foundation technology. But there's also an electrical first, and that's if you can see on the slide there where it says connection. So Blythe was the first offshore wind project to connect using 66 kV export cables. And this is one of the big recent moves in the electrical system in offshore wind. So previously, particularly in the inter-array of the turbines, 33 kV was the voltage that many of the early wind farms used. But as the turbines are getting bigger and bigger, it didn't make sense to use that voltage anymore. So as the megawatts of the turbine were increasing, we wanted to use a higher voltage. And this was particularly useful for keeping the cable size more manageable, keeping the cable losses under control as well. So the beauty about the demonstration project is that it just gives the stakeholders confidence that the technology works. You know, they're not just seeing it on a simulation, they're seeing it working with real hardware. So one of the major changes in recent years, I think. This slide focuses on another quite often discussed challenge, and that is AC versus DC. So there's an interesting article that was written in, I think, 2014 by Colin Davidson. So Colin is, he works at Alstom Grid in the UK, very experienced technology champion in HVDC and electrical conversion. And he talks quite interestingly about the considerations when you're choosing your transmission technology. There are some subtleties to whether you go for AC or DC. What I've tried to do is distill that into a single slide today. So hopefully I've captured the main points. But essentially, AC is what most offshore wind farms use at the moment. It's widely used in offshore wind transmission, and it's also perceived to be a more reliable technology, a more reliable solution. One of the advantages of AC technology is it can be stepped up and down quite easily using transformers, so the voltage can be stepped up and down easily. But the main drawback, particularly when your wind farm is transmitting over a further distance, so it's further from shore, further from the collection point, there are significant losses that can be experienced over those long cable distances, and that leads to additional operating expenditure because you've effectively got to boost the voltage along the way. So that's where HVDC solutions become a little bit more attractive. The drawback to HVDC solutions are the capital expenditure is generally higher than AC solutions, but over a longer transmission distance, there comes like a crossover point where the increase in the capex of a HVDC solution is outweighed by the increased operational expenditure, the increased OPEX of the AC solution. And that's when the HVDC solution is sometimes seen to be the better techno-economic solution. So that's essentially the consideration that goes into these things. And that crossover point isn't fixed. So you can't say, you know, if your offshore wind farm is greater than 100 kilometers offshore, it's always going to be HVDC, because the factors that drive that techno-economic study will change, and therefore that crossover point will move. But it's kind of in that range, you know, 80 kilometers, 100 kilometers. Sometimes it's a little bit less. And then you may have a technology breakthrough in one area and it moves. But that's kind of the story. And then the final bit I was going to talk about with cables and transmission technology was actually utilizing DC within the wind farm itself. So in this particular example, what we've looked at the Catapult is, can we use DC within the wind farm? Can we either reduce or eliminate substations? So there's a number of steps that we've gone through here where we've found that, you know, we can potentially reduce costs by 15%, which is quite significant. We've done some simulations on how you might design a modular multi-level converter. We had some challenges with the frequencies involved and the switching losses, but as a result of that, we've developed a new control algorithm. And basically that technology now needs some demonstration. So we do believe it's possible, and you know, the use of DC within the wind farm as well as the connecting the wind farms together or connecting the wind farms to shore is certainly well worth considering. So now I'm going to move on to ancillary service provision. So historically, wind turbines have been fairly simplistic energy conversion devices, or they've been seen to be from the wider energy system. So basically you're converting wind energy and you're providing that as electricity to a given set of rules, and basically you're following other assets that are controlling and managing the grid network. However, with the transition away from the traditional power stations, the very carbon-based power stations, which historically have been used for controlling the grid and restarting the grid, so the black start generators forming the grid and providing some of the services, that's not going to be there anymore, because obviously we're trying to move away from that and get a greener, more sustainable energy system. So that provides an opportunity for wind turbines to provide some of these services. So when I talk about services, I'm talking about things like synthetic inertia, frequency support. This particular slide actually focuses on black start and grid forming. So essentially what we're saying here is a wind farm with some battery capability, some energy storage capability could potentially provide a black start capability for a network, and ultimately get the network up and running again after such a condition. It is possible, and it's something that the industry is looking at. And this slide here goes into an example of a particular project that we carried out maybe 2 or 3 years ago, where we were looking at control and protocols for offshore wind black start. So it was based on our 7 megawatt demonstration turbine at Leavenmouth, which is on the east coast of Scotland. So there's some schematics there on the slide. And so what we did is effectively we carried out objectives 1 and 3, which was looking at the development of protocols and the simulation of certain scenarios. The next stage that we'd like to do is to actually demonstrate some of that, but that isn't a project at the moment. The other thing I wanted to point out here is, if you look at the bottom right of the slide, you'll see the auxiliary power. So if you think about a black start, you obviously need some kind of power supply to get the wind turbine or wind farm auxiliary powers and control energized so that they can fire up the wider network. So you may consider it a UPS sort of solution. We've got diesel generator written there. What's actually becoming more and more attractive as a potential solution is hydrogen. So using hydrogen fuel cells as effectively your UPS or diesel generator replacement, because obviously it's much more green and sustainable than a diesel generator. So I wouldn't be surprised if there's projects in the near future in that space. So now I'm going to move on to floating wind. So as I said in the beginning of my presentation, the floating wind is becoming more and more important to our offshore wind sector. And from an electrical point of view, we're particularly worried is maybe not the right word, but we're particularly interested in the dynamic cable elements. So clearly a floating platform, if you're going to connect that wind energy in the electrical vector, then you're going to have a dynamic cable. And so first and foremost, we're interested in modeling that. So this slide here is quite busy. I'm not going to go into huge amounts of detail, but essentially this is a model that we've developed over the last few years. And what we're looking at here is in the top left, we're trying to model the mechanical movement of the floating offshore wind platform and the dynamic cable, and model the subsequent loads and forces that will create. Top right, we're looking at combining that with an FEA analysis to produce a time history of stresses. Bottom left, we're then using that information to do some damage calculations and to predict some propagation of electrical phenomena like treeing. And then in the bottom right, we're trying to see how that mechanical fatigue potentially increases the overall fatigue of the cable from an electrical perspective, with a particular emphasis on the insulation properties and the potential insulation breakdown of a dynamic cable. So extremely interesting stuff, but quite complicated, quite challenging. So I guess that's the first stage, you know, how well can we model dynamic cables? And then the second stage is how well can we validate them? How well can we test those dynamic cables? So this slide here shows a dynamic cable test rig that we have at ORE Catapult. So we've used this on quite a few projects now, where we actually take cable samples and exercise them both mechanically and electrically. We've also got the ability to put this rig in submerge it in water as well, submerge it in seawater. So that there's a possibility to do 3 things all at the same time. So electrical, mechanical, and submerged conditions all acting simultaneously. So the beauty about this is, I guess, is twofold. One, we can validate actual cable designs, so cable samples. But secondly, we can also validate the models that we've produced as well and get confidence in those. So after a few iterations, you're getting quite a capable combination of validation and modeling of dynamic cables. There's a web link there if you're more interested in seeing that rig. There's quite a nice video on the ORE Catapult website. The other bit I wanted to talk about was subsea collectors. So floating wind requires dynamic cables, as I've said, but it also requires floating substations, or at least you'd think so. Floating substations aren't necessarily that easy to realize, and they've also got the challenge of the dynamic cable. So something that's also being looked at, there's some interesting work and research in organizations like Sintef in Norway. They're looking at subsea collector technology, where you actually put some of the electrical equipment on the seabed. Now that would still require a dynamic cable from the wind turbine itself, but the actual transmission cable back to shore is no longer dynamic. It's static on the seabed. And that I guess is the operation critical part, because if you lose your transmission cable, you lose your wind farm. If you lose a dynamic cable from an individual turbine, you've still got the other turbines in the wind farm. So quite an interesting thing to look at. And it's also like offshore wind currently is. So in a fixed foundation wind farm, your cables are going to be static. So there are advantages to going or considering this route. Okay, so I'm getting into the last couple of parts of my presentation now. So I quickly wanted to show you the evolution of the energy system. So this is a slide I've used before, and it shows you how our current energy system, with some numbers based on UK, the UK energy system, is evolving from, say, 11 gigawatts of offshore wind at the moment, quite a lot of dependency on natural gas and fuel engine vehicles. And we're moving towards much more offshore wind, much less dependency on natural gas, a lot more electrical applications such as electrical vehicles, much less dependency on fossil fuels. And what that does is it throws up two big challenges, two big outcomes. Firstly, how are you going to connect a huge amount of offshore wind into the network? And the other thing is, what technologies are you potentially going to use to do that? So the first one is connecting large amounts of wind. And one of the things that we have considered is using hydrogen as an energy vector. So you'll probably see hydrogen is becoming more and more topical as we talk about future integration of wind, future energy systems. This particular project here from the Catapult, we're actually using our demonstration turbine to power an electrolyzer. So we're producing green hydrogen. And then we're going to use that electrolyzer to feed a number of homes in the Levermouth region. So phase 1 is 300 homes, phase 2 is 1,000 homes. So essentially we're proving out the process, we're proving out the effectiveness of green hydrogen production. And I guess the next stage would be, how does that fit into a wider energy system? And with that in mind, this is another project that we're looking at, which is looking at how do we have a local energy community which uses multiple energy sources, different energy vectors in terms of electricity and hydrogen, to basically create an energy system solution which is sustainable, which is net zero in effect. So what this particular project does, it looks at separating the different elements into different cells. So we have a wind power cell, we've got a PV and storage cell, we've got a hydrogen cell, and other ones, as you can see on that diagram. But one of the things that's useful about it is it's scalable. And I would suggest that national and international energy system solutions are going to follow a similar path, follow similar challenges, of course, but it just gives you an insight into where our energy system solutions might be heading in the coming decades. The last part of my presentation was a couple of snippets of what might occur in the future. And the first thing I've picked out is energy islands. You may have heard about this. So one of the comments I've got in my notes here is that it's no longer just a TV fantasy. So if I don't know whether the audience you've ever seen the TV program Thunderbirds, but they had Tracy Island, and it, myself and my colleagues often think this energy island, it's a bit like it's come from a program such as that, something futuristic, but it is happening. You know, and certainly in Denmark, organizations like Energinet has started work on developing these islands in the North Sea and Baltic Sea. And as it says on the slide, this is a potential solution for a supergrid, you know, a North Sea offshore network. And it provides a natural home for substations as well as O&M facilities for those far from shore offshore wind farms. And also, if you get a chance to look up the Horizon 2020 project called Promotion, which recently finished, that was looking at using meshed HVDC as a transmission network. So again, energy islands are a way of realizing some of that technology, some of that solution. And then the final piece was superconducting technology. So this is a project that Catapult are working on with the University of Strathclyde and Supernode Limited. We've recently published an article, which is in the link here at the bottom of the slide, how we've done a cost comparison between traditional HVDC transmission technologies and using superconducting technology like superconducting cables, HCS cables, to provide that solution. And the results are quite encouraging. They show that the superconducting solution can compete with the more traditional HVDC technologies. So it should be considered in future networks, because the real benefit of something like a superconducting technology is it significantly reduces cable losses, because you're operating in that superconducting space, and it significantly increases the capacity of the cable as well. So if you think about trying to connect large amounts of offshore wind in the North Sea by 2050, you're talking about 500 gigawatts across Europe. Then that's a huge demand, a huge challenge for the electrical infrastructure. So maybe breakthrough technologies like HCS cables can help in that journey. Right, I think my time's pretty much up. So just in conclusion, hopefully I've shown you in the last 30 minutes how offshore wind has come so far in the last 20 years. If I've taken you from the 2 turbines in Blythe to the futuristic energy islands and superconducting cables. I think there's a huge amount we can do in the next 30 years. So if you think about how far we've come in the last 20 years, just imagine how far we can go in the next 30 years. I'm hoping you can all be part of that journey. I'm sure for one that it's going to be very exciting. So I'll leave it there, and I guess are there time for questions?
Hi, Paul, thank you. Right now we're going to have another keynote speaker and following one more presentation before the Q&A.
No problem.
Are you able to stay till then?
Yes, no, that's fine. I'm fine.
Okay, perfect. So thank you, Paul. Our second keynote speaker is Francesco Boscolo. He's a researcher within the offshore energy area in Tecnalia. He has civil and environmental background with an offshore renewable energy education, specialized in mooring system and dynamic cable design. His presentation is called The Design of Dynamic Cable for Floating Platforms. Thank you, Francesco. I think you are muted.
Hello.
Hello.
Thank you for the presentation. I'm going to share the presentation. Actually, I don't know how.
It's okay. Do you have the PowerPoint open?
Yeah.
On the lower part of the PowerPoint, there's a small sort of screen that says slideshow. Right on the left of the minus and plus signs for the Zoom.
Yeah.
Okay, click there and it should be able to appear.
Francesco, you should be able to share the screen from the Zoom app as well first.
Oh, okay. I think it's easier.
If not through the PowerPoint, maybe it's easier as well. So if you just come onto the Zoom app, at the bottom of the screen, there should be a share screen option, along with next to the chat and the other details in the Zoom app.
Okay, okay. Yes.
Yeah. So just go to share screen and choose
okay.
the PowerPoint. Perfect.
Okay, sorry for the late.
It's okay. You just need to go to presentation mode. Perfect. That's perfect.
Okay.
Thank you.
You can see? Okay. Okay, hello to everyone. I'm Francesco Boscolo, and I work in private research center, Tecnalia, Spain. And I've been involved in several projects about the design of mooring system for floating platforms and also design of flexible cables. So I start with the presentation. I started talking about what is the power cable. The power cable has a mission to transmit energy and data from the platform, between the platforms and the onshore infrastructure. So data and energy. There are several. The power cable can have several layouts in function of the number of devices, the floating platforms, the total power, and the distance to the onshore grid. It could be a direct connection to the coast, or can be employed intermediate stage when the cable can simply be grouped, or also we can have a voltage transformation stage, like in an offshore substation. Some conceptual images: connection to hub, connection to offshore substation. Talking about a farm or several floating platforms, it's common to have a voltage transformation stage. In this case, the power cable can be distinguished in inter-array cables from the energy generation platform and the substation, and export cable from the substation to the coast. On the left, we see the inter-array cable on both image, and then on the right, the export cable to the coast. So there are inter-array cable and export cable are cable of different composition, different weight, different diameter. The power cable internal structure can be composed on different conductors with different cross-section insulation, and also with fiber optic wires for the data transmissions. Depending on the typology of the cable segment, static or dynamic, the cable can have a single or double armor in function of the loads, of the environmental loads, and on the motion of the platform that it shall withstand. An example of static cable on the left dynamic cable on the right where we can appreciate the double wire armor. And now let's talk about the dynamic cable. Dynamic cables tend to be the segment of the power cable that going directly from the floating platform to the seabed. That could be a simple point fixed on the seabed, or a hub, or a connector that normally is connected to the static cable. So the dynamic of the floating platform and the environmental loads make that the design of dynamic cable is fundamental to perform the primary function of the electrical evacuation system. That is, as I said before, be a physical medium from energy and data transmission. So dynamic cable is supposed to be the only segment of power cable directly subjected to the platform motions. So that's why it shall be treated differently from the static cable. The dynamic cable can have different configuration that shall satisfy the requirement and the functionalities of the power cable. That are to keep the integrity of the power cable, the famous relationship curvature tension, to avoid any contact with the other external elements like platform mooring system or other cables, to avoid any contact with the seabed, and then to keep a minimum clearance with the water line. As I resume, to keep the integrity of the power cable and to keep a minimum distance of the cable from other elements. The relationship between curvature and tension is the most important characteristic of the power cable that the designer need. It's called the cable capacity curve. It's a curve that show the relationship between tension and curvature. It's a curve that normally there are one different curve for each design condition. In this case, in this example, there are one for ultimate limit states and installation, another one for accidental limit states. The most important fact is that this curve is fundamental for the design, and it's provided only by the cable manufacturer. So, and normally the designer get the cable capacity curve only when after the purchase of the cable. So it's a critical point, and there are some rules that can provide that provide some default curve or some default formula to get the tension function of the curvature in absence of the real capacity curve. But the objective of the critical point of the design is to get the real cable capacity curve. So there are some, as I said before, there are a large number of different configurations for dynamic cable. The selection, the designer can select one among them depending on several factors: the mid-ocean condition, included by the bathymetry, the platform draft and motions, the power cable characteristics, and also the project life and the operation maintenance strategy. Now I'm going to show some configuration. There is the basic one, a catenary configuration, like for example, similar to that one of a mooring system. Lazy S with a buoy tethered to the ground by a tether cable, a wire. Then a steep S that is very similar. Lazy wave, that is I think the most famous one, with some floaters distributed along the cable. Steep wave, pliant wave. This is very similar to the lazy wave, but with the segment of the cable tethered to the ground. double whale that can be applied to different configuration, but using several waves shape in the cable, and weight added wave. Now let's go. I'm going to talk about the lazy wave configuration. Lazy wave configuration is the most popular because for the floating platform, because it's a viable solution to improve fatigue and strength performance of the cable, responding to the motion of the floating platform and then to the loads of the environment directly applied to the cable. This is an example when we can appreciate the critical point, the critical point of the cable, the angle of point, the seg band, the arc band, and the touch band point, that is the segment of the cable touching the ground. That are the critical section of the lazy wave configuration. The seg band, the arc band, the touch band point. Of course, the red line is the cable uncovered, and the blue line is the cable covered by the distributed floater that in the first stage of the design, the distributed floater are designed like a continuing segment. Talking about the metocean condition, there are some we can distinguish between indirect loads that are wind, waves, and current that acting to the floating platform and in turn to the dynamic cable through the motion of the angle of point. And then we can say that the first order motions in Hive surges way direction of the platform are mainly translated into Hive motion of the segment. Different is behavior for the second order motion when that give the time to the lazy wave to respond globally. The motion in Hive surgeon way direction of the platform turn into both horizontal or vertical motion of both segment, the arc band and the segment. And then there are direct loads that are environmental load that act directly to the cable, to the current. The current is important in about both direction of the current and the vertical profile of current that are fundamental for the design of the cable. So current, direction, and vertical profile are to be taken in account by the designer for the orientation of the cable and the vertical profile of the cable. This is an example of the vertical profile of the current that not only change the velocity, the horizontal axis in function of the depth, the vertical axis, but also change the direction, because go from at 20 meters, reach the maximum of the velocity in one direction, and at 100 meters, reach the maximum of the current in the other direction. Design methodology. In the design of the dynamic cable, the designer shall take into account different design conditions in order to find a configuration for the cable that be compliant for the requirement of the power cable. Design condition in installation, during the installation phases, transport installation, and during operation. The different limit states: service, ultimate, fatigue, and accident. It's important to note that the cable manufacturer may provide different requirements. It means different cable capacity curve for each, as I showed before, for each stage of the design, of the life of the project. A question that the designer cannot respond at the beginning of the state of the design is if the ultimate limit state or the fatigue limit state driving the design of the dynamic cable. We don't know what's the worst, and we could find an answer to this question only during the design. And then another question: accidental limit states. It's mandatory or optional. The designer, it's a selection choose of the designer to design the cable compliant to the condition when there is a line on the line moving system broken, and when there is the drift of the floating platform that exceed a certain value. In this case, the designer can choose if the umbilical cable keep the integrity, the umbilical cable configuration keep the integrity of the power cable or not. This is a proposal of methodology that here in Tecnalia we use. There are the design distinguished in different stages: initial, basic design, design verification, and final. When we apply different analysis, static analysis using an in-house model that we have, and then dynamic analysis in frequency domain or in time domain using some commercial software for the dynamic cable design. Using the first part, we use only some design load cases, call it the driving design load cases. Then in the design verification, we use all the design load cases. And then the final design where there is the detailed design of the cable configuration and the verification of commercial items, the auxiliary elements like the distributed floaters of the lazy wave shape, or the cable protection on the sheet bed, or the band stiffener. It's important that it's an iterative design, and in every point and every stage we can go back and start from the initial design again. Static analysis, as I said, we use a tool, an in-house tool that we develop in Tecnalia in order to perform a static analysis of the cable and select a set of acceptable configuration. So we treat the dynamic cable like several consecutive segments of catenary curves with positive and negative buoyancy, and we applied in 2D. It's a 2D system. We applied a motion of the platform at the end of point. In this case, that I show in the picture, there are 5 points. In each condition, we calculated the curvature and the tension, and so we can, by varying some call it the design parameters, like the distance of the lazy wave shape from the seabed and from the waterline, and the projection of the wall cable, dynamic cable, on the seabed, we can find a set of acceptable cable configurations, and then with this set of combinations, we can pass to the second step, that is the dynamic analysis by using some commercial software, like for example Orcaflex. Okay. in the first stage, there is also the modal analysis that is realized by using OrcaFlex, when we can see the mode shapes of the cable in function of the frequency, and we can the goal of the designer is to make that the cable is not it's not moving a lot in the same natural frequency of the platform through the angle of point. Then the dynamic analysis in time domain, using OrcaFlex by or China, we can select some different irregular or irregular C states and building the model. This is an example, and see the behavior of the model during a dynamic simulation of several durations. And that's it. So the presentation is finished. And
yes. Thank you, Francesco. Our last speaker of the morning session is Will Brindley. He's from Catapult, and his presentation is called Dynamic Cable Design. Will, are you there?
I'm there, thank you, yes. Is there a way to show my camera?
If you want to, if not, it's okay.
There we are. Not used to Teams so much here. Okay, and just let me know if you can see my presentation there as well.
Okay, not yet. We can see your screen, but not the presentation. Oh, okay, perfect. That's perfect. Thank you.
And I'll get this out of the way. Nobody wants to see my face. All right. Okay, so yeah, I'm going to sort of follow on a bit from what the previous presentations talked about, and I guess it's maybe a little bit more practical and a little bit less research focused, to give you an overview of dynamic cables and I guess what you need to think about in terms of a long-term reliability. So this is our static array, about 30 turbines, so about 0.5 gigawatt. We've got a static cable here with some armor wire. We've got the cable cores, fiber optic, and that's the connection into, in this case, a monopile. So a fairly simple connection. It's got a bend stiffener or a bend restrictor. It goes through some protection to hopefully stop it from abrading on the seabed. And then separated by about 2 kilometers, these cables are strung together on the wind turbines. And inside the turbine itself, the cable is connected via some joints to the switchgear. These cables, probably very well publicized, aren't particularly reliable. They fail a lot, certainly in proportion to the capital cost. So for example, if you had a wind farm like this over a lifetime, you might expect on average about 4 cable failures. So a very high failure rate, fairly significant downtime, because ultimately this is what carries your power. So there's quite a big consequence if you can't send that power back to shore. And an analysis of most of the failures indicates that it's a installation largely and a little bit of manufacturing issues, with relatively few failures relating to sort of long-term wear out. But that might just represent the fact that most of these cables are less than 10 years old, so we've yet to see the wear out failures. So what we might see in the next 10 years is a lot of the long-term issues are addressed, or sorry, the installation issues are addressed, and then we start to see long-term wear out from other causes. So that's our static field. Now what's our dynamic array look like? Well, it's a lot more complex. We've got lots of mooring lines. The cables themselves have a lazy wave. So there's a bit more complexity here and a bit more to think about in terms of the design of these systems. So this is what the system looks like in this case in OrcaFlex. So we've got a turbine on top. We've got a foundation, lots of different options, but the current candidate that looks to be winning out, certainly in the UK sector, is a steel semi-submersible. So that's what I've pictured here. In this case, there's 3 chain mirroring lines on that semi-submersible, and then there's a power cable going in and a power cable going out. So it's part of a bigger string. So 2 lazy waves in this case. So how do we design this? So I thought I'd make a nice sort of process for designing this system. So you've got this cable, we've got all the cores, the armor wire, and so on. When we put this into our global model, unless we're looking at fatigue, typically we can characterize it by basically 3 simple parameters. So the outer diameter, that defines how it behaves when it's contacting the seabed, and also the buoyancy. So the outer diameter is our first parameter. The other thing that we're interested in is the bending stiffness. So that will dictate how much curvature the cable sees. And then the final thing that we input is the unit weight per meter. So how heavy is the cable? And again, that sort of dictates the catenary that we see from the cable. So some fairly basic inputs. And in this case, we start off with a basic catenary. So what we try and do here is we get the cable to sit down at about 5 degrees, and we don't put any buoyancy on, we just see if it works as a catenary. Normally this won't work in anything other than very, very benign environments, but it's a good starting point. So in this case, we're applying wave, winds, and currents to our semi-submersible, and the wind turbine itself is seeing some load. And what that does is it offsets this quite fast, and this is 100 meters water depth. The only thing stopping it offsetting is the mirroring line, and what we got is about 25 meters of offset, so about a quarter of the water depth it moves. And when it moves, one line becomes slack and the other line becomes taut. And in this case, because it's a catenary and we don't like it in these kind of conditions in the North Sea, we've got one line that's going way over tensioned, lots of problems with seabed abrasion, and the other line which has been way overbent. So this doesn't work, so we need to fix it. So the first thing we do is we add some buoyancy. So in this case, I've added 5 100 kilogram net buoys, so 100 kilograms up force. And what we can see is that it's helping us a little bit, but this line is still going straight and this line is still overbent. So we've not added enough buoyancy here. So we need to add more buoyancy. So in this case, I've added 10 200 kilogram buoys. So it's lots of force going up the way. And in this case, we've added too much buoyancy. So our waves are now forcing the buoys, moving it around a lot. And particularly in this area, you've got lots of horrible bending dynamic motion. So we don't want the buoys too high up, and we also don't want the buoys too low that we had before. So we've got a Goldilocks system here where we've got about 10 buoys. It's a nice lazy wave in the middle of the water column. It moves relatively nicely, and we're not over tensioning any lines too much. So we've got reasonably okay. The next problem that we have is we haven't put a bend stiffener in. So without a bend stiffener, this bit is going to see a lot of dynamic motion and bending right at the connection. So if you try and terminate that cable there, it will either wear very badly with whatever it's connected to, or it'll have a big bending radius. So that's not very good. So instead, what we want to have a bend stiffener like this, which is basically a solid block of plastic, usually polyurethane. It's a big tube that tapers, and because of that taper, it gradually changes the curvature of the cable as it goes down. So you don't have any hot spots of a big bit of curvature or motion. It's nice and smoothly transitioned. And typically that's about 5 meters in this case, but you'd design the length and the diameter of that tube to give you a nice performance. And usually there's a bit of coupling. So you design your cable, you put in the bend stiffener, and then you refine the bend stiffener design as you go. Okay, so we've got a reasonably good design. Now what we're going to do, I'm just going to pause this here, is we're going to apply a current. This is called a cross current case. So our wind and wave are coming towards us. So the vessel's going to move towards us here in the line of the cables. But the current doesn't always follow the wind and waves. The current often follows the tides. So it's not uncommon to have a current going at 90 degrees to the winds and waves. And what that means is because these attract quite a lot of load and they're not all that, they're under very little tension, the dynamic cables can move really quite a lot in response to wind and wave. So what we'll see is that in many cases with relatively high currents or even moderate currents like you see in the North Sea, our cables move a lot. And that's a problem because it means that the cable is going to be dragging on the seabed, it's going to be wearing on the seabed, and eventually it might migrate out of position. So it's really not a good thing for this to happen. So a solution to this, which we see in a lot of cases, is tethers, which are basically clamped and then tied back to the seabed with some wires. And that stops the cables moving too much. So it limits how much they can move sideways and also forward and back with the current. So that's a solution that's very often used. And then this is our final tethered lazy wave design. So probably this is what the process that you go to in what we call FEED, so front-end engineering design. When you design one of these systems, this is how you roughly come up with a design. And then you go through many more steps, looking at fatigue and other characteristics of the cable to make sure your design's okay. But this is roughly what you come up with, at least to size your components. So we have our cable now, we've got some buoyancy, we've got the bend stiffener, we've usually got some kind of outer sheath to protect against wear at the seabed. And what are we interested in? Well, there's a few bits that you really need to focus on to make sure these last. So making sure it's not moving too much in the seabed, so you might need a tether. Making sure it's not bending too much. Typically it'll be around this region that you'll see the worst bends. If it bends too much, you'll damage your cables and potentially cause failure. So that's a static extreme bend, but also you look at fatigue. So how many cycles of bends do you have? And then the other thing that you look at, which tends to cause failure, is two parts. One is the top of the bend stiffener, where it connects into what's called a J tube, so it connects into the fixed platform or the fixed structure. That mechanism can often fail because of the way these are installed. Sometimes that isn't particularly robust. So that's one area that can fail. The other area is typically right at the tip of the bend stiffener, where the cable is moving back and forwards, and that tends to cause some bending and abrasion, local wear issues there. So you can often see failures right at the edge of the bend stiffener. And these are some real problems that we've seen on cables. So I think Paul talked about water treeing. So in the insulation itself, if you get too much water and in certain conditions, you can get water tree growth. If you haven't designed the cables properly thermally, you can get some thermal issues. If we go back to this, particularly around the J tube or areas where you've got lots of insulation, or if the cable's in air, there can be too much heat buildup in the cable, and you can get some thermal degradation or overheating. Probably the most fatigue sensitive components of these systems are the copper. So you've got these screen wires and you've got the copper cores. When you bend back and forwards, that bending can cause fatigue. And something to think about here as well, it's not just a pure, you've got a bar, you're bending it fatigue. These wires are all sitting on top of each other. As they sit on top of each other, they contact, and that small area of contact can start fatigue crack, and that's called fretting. So that's another thing you've got to think about. Fiber optics, if you damage those, they can actually result in failure of the whole cable. So that's another problem area. Armor wires, steel, nice and robust, but steel still corrodes and it fatigues. So that's another area that can fail. And if you smack the armor wire with a dropped object, an anchor, that can also cause failure of the armor wire. In this case, that's impact damage. And finally, the sheath itself, if that isn't properly designed or it's seeing too much strain, it can also crack and damage as well. And if the sheath damages, that can let water in, which can then cause problems with the other components in terms of corrosion. So how do we ensure reliability over the life cycle? Well, it all really starts with design. Pretty much all problems can be solved at design, or at least getting the documents and the specifications right. So that's the most important part. A key part of that is looking back at previous integrity issues. So I think there's a question about risers. What's applicable from what we know in oil and gas about risers and a lot of experience in risers is basically you've got the sheath and the armor wire is quite similar. Risers have flat armor wire, these have rounded, but essentially it's pretty similar. So you can learn a lot about the behavior of this layer from risers. And oil and gas umbilicals, there's a lot of experience of power cables, so we can learn a lot about those to find out what we're expecting to happen. And the data, although it's quite sparse from oil and gas umbilicals, is that the cables are certainly the weakest part, the part that's most likely to fail. So that's the area you need to look at in your fatigue and upper assessments. Manufacturing, we do see quite a lot of issues, and that's it is being improved, but there's more work needed to make sure we can produce particularly cable cores of good quality. Insulation, that is the cause of most of the static fixed cables failures, so we expect that to still be the case with dynamic cables. So control of the installation process and planning, quality assurance is the key part there. And then operation, well, what we expect to cause failure I've discussed, but this is all speculative, we just don't have the data to say yet. But certainly we feel that fatigue and insulation degradation is the most likely cause of long-term failure. So how do you make sure that cables are okay? Well, you can test them. So this is our dynamic test rig, and this is an Orcaflex model of that test rig. And essentially you can just bend the cable as it would be bent in service. So you choose a radius, and I think in this case it's about a 2 meter bend radius, and you give it about 1 million cycles, so many months of testing with this bend radius. And then when you finish, you break the cable down, so you cut it into layers and see if anything's broken. Quite rough test actually, but there are ways also that you can monitor the cable during a test to validate things like your bend stiffness model and also your fatigue model as well. And this is what we're working towards, it's a final way of ensuring cable integrity. So we take all the models I talked about, the global model as well as a local model, as well as models of things like insulation, water treeing, thermal degradation, fatigue models. You take test data to validate those models to make sure that they're sensible and they characterize what's really going to happen. And then you make sure you put sensors on your real system. So there's many ways of monitoring the cable through strain, vibration, temperature, and electrical monitoring. And you integrate all this together, and you use that then to track your cable performance. So how's it fatiguing? Is it behaving as we expect? And ultimately, 25 years into the life, you can ask, well, do we need to replace the cable, or can we run it for another 10 years? So that is where the future is heading for this technology. And I guess a final thing I want to leave on is when you're looking at the cable failure, it's not just the cable you've got to be interested in. It's also the mirroring line. So in this case, we've got an array of 20 turbines. Each of them have a mirroring line. If you then fail one of those mirroring lines, you also expect to fail the cable as well. So mirroring failure is pretty common. It's not unexpected to fail at least one line in an array like this. If you fail one line, that can then lead to failure of the other lines because it's in an unusual condition. You can pull out your anchor. And then that'll drag your cable across, break the cable, but also potentially break a whole series of mirrorings and cables in that array. So quite a high risk scenario. This is the kind of chain we're talking about for mirroring these facilities. So huge chain, about the size of a person's torso in many cases, this chain. So it's very big stuff. You don't want that running over all your subsea assets. You can have a very expensive failure. We've seen these kind of failures a lot in the oil and gas industry. Excuse me. So it's something to watch out for in floating wind as well, and make sure your whole system is designed to accommodate this kind of incident. And that's towards the end there, yes, this can go walkabout really quite quickly. I think you're talking about a few hours in a storm in the North Sea. There's no way to really stop an asset moving. It's not safe for a boat to get too close to that, so it's very difficult to stop this once it happens. And I think that's my presentation.
you. Well, certainly the last video is a little bit scary. Was that just a simulation, or did it happen at some point?
It's just a simulation. There's not been enough floating wind farms to see if it happened, but you can certainly look up the Griffin FPSO incident or the Banff FPSO incident, and about 10 more incidents in oil and gas where you can see this thing happening, where a mooring line fails and your whole billion-pound subsea infrastructure gets destroyed because of this one chain failure.
Okay, it's certainly something to take into consideration.
For sure, yeah.
Now we will start the Q&A session. I will ask the speakers, both Francesco and Paul, if you can also turn on your cameras. And I see that some of the questions have already been answered through the application. Give me 1 second, I will check. Okay, there are no questions for the moment. I do have a lot of questions, but if any of the panelists would like to ask something, please feel free to jump in. In the meantime, I will start with my questions. For Paul, for example, when you mentioned integrating hydrogen, but you mentioned mainly using hydrogen fuel cells. Have you analyzed the whole integration of hydrogen, of production of hydrogen within the electrical system? Do you need more substations if you incorporate hydrogen into the system, into the offshore wind farm? How does the whole integration of the system affects the electrical network?
Yeah, thanks, Amarina. I mean, those questions you've just posed are all very good questions, and essentially, there's a huge amount of work to do if we're going to use hydrogen as an energy vector to help us realize, 80 gigawatts of offshore wind in the UK, 500 gigawatts in Europe. The example I gave for the fuel cell was just a very specific thing where we could potentially use a hydrogen fuel cell as a energy storage device to help us get a black start situation underway. If the turbine itself was being used, or the wind farm. But I mean, the wider questions around how do we integrate hydrogen? When is it best to use it as a storage solution? When should we use it as a transmission vector? Should we convert things back to electricity? When should we do that? How do we deal with the production of it? Is it scalable? There's a huge amount of questions that we still need to answer, but I guess the work has started. So we haven't got the answers, and of course it's going to take many researchers and many organizations working together to answer these questions, but we've started the journey, let's say.
Okay, thank you. If none of the panelists have any more questions, I will continue with mine. Related to the depth, the maximum depth that we can still use the cables without having too much trouble. Are any of you studying how to move forward into depths that are higher than 100 meters? Right now, there are a lot of countries like Spain, Portugal, even in Latin America, we have some participants from there. And because the continental platform is short, they have to move into deeper waters. And are any of you making any studies on how to tackle those problems?
I started making some little research about the utilization of different material for the construction of the cable, light material that can give the same strength and stiffness of the cable, of the actual cable, of the present cable, but giving less weight. But I didn't focus a lot about the using of a cable in deep water.
Okay, Paul, you mentioned the superconductors. Is it correct to assume that the superconductor will have a smaller diameter than the normal cable?
I guess if you do a like for like comparison, so I mean a superconductor cable, by definition, if you're expecting it to carry the same amount of current, then it should be smaller. But of course, then if you're looking to use it on a widespread scale to connect a European network, for example, you may just want to make it a similar size but with a bigger capacity. But I guess in theory, if you're looking for a superconducting cable to carry the same amount of power or the same amount of current, then dimensionally it should be smaller.
Okay, thank you. So we don't. Yeah, we have
1 second. Yeah.
some more questions. Okay.
Just a follow up.
Yes.
Hello, Marina. Sorry. Yeah, just to follow up on the superconducting question you had, Paul. What is the main challenge right now when it comes to replacing the existing cables with superconducting? Like, what is the biggest challenge for practically applying a superconducting cable? I'm not an expert on the field at all, but I just wanted to know what, according to you at least, is the biggest challenge that has to be overcome for actually applying superconducting cable in a practical sense.
Yeah. So I guess, well, first and foremost, I'm not sure whether the superconducting cables are being looked at to replace cables. That they're seen as an alternative to build out infrastructure that doesn't exist yet. And I guess that's one of the challenges we have in the UK and other countries, that the electrical infrastructure doesn't exist to connect 80 gigawatts in the UK's case of offshore wind. So in terms of, is it a viable solution for the new infrastructure that needs to be built, the biggest challenge is probably going to be the usual suspects. So it's things like the cost and the reliability. Some people also get nervous about the cooling aspect, because obviously HDS, high temperature superconductor technology, needs to be kept very, very cold, and how reliable is that? How do you do that over a long transmission distance? Now, it is technically feasible, but I guess because it's unproven technology, the operational reliability of that technology is not known at the moment.
One question also related to what you just mentioned. I wanted to ask you, how do you tackle the network, the onshore network that has to be expanded? In most cases, even here in Portugal, when we're trying to promote offshore wind or any kind of offshore renewables, the main issue we have is, okay, even if we promote the wind farm and we have it tomorrow and we're not able to connect it, we don't have enough electrical infrastructure. Does that always start from the government, or from the companies? There has been some kind of movement to incentivize the government to do it?
Yeah, it's a mixture of things, Marina. I think the UK shares similar challenges to Portugal, and I'm sure it's not unusual in many other European member states as well. If you remember at the start of my presentation, I said I didn't touch upon market stroke regulatory type evolution, because that's a topic in itself, and often, particularly in the expansion of electrical networks, it's the market and the regulatory hurdles, if you like, that the biggest ones. I think in the past, electricity companies, whether they're transmission system operators or distribution system operators, they've not always had the best reputation for moving particularly quickly. I think there's been movement in that space, and there needs to be, because there's a big challenge, and we want to try and avoid the electrical infrastructure being the big bottleneck to getting all this, certainly in the UK, all the offshore wind connected into the energy system. I mean, that's another reason why we're looking at hydrogen, because I think there's kind of a realization, maybe a sort of emerging consensus, that actually we're not going to connect 80 gigawatts of offshore wind into the electrical network, it's not going to happen. So we need other energy vectors to help us do that, and that's why we're looking at hydrogen.
Okay, I have a question for Will. You mentioned that when you have failure, you have more or less a downtime of 38 days for the replacement of the cable. How many meters are we talking about of the replacement part? Are we talking just of 38 days to change 1 meter of cable, or we're talking a whole line between one turbine and the other?
Good point. I'm not. You need to have a look at where the data comes from that. I mean, when you have a failure, you have two options. One is that you can, I mean, typically a failure will be quite localized depending on what the failure mode is. But say you've got I don't know, electrical breakdown or a bit of bad manufacturing that's caused a failure. That'll typically only affect a few meters. So from some testing, you can localize where that is. So say it's 820 meters from your turbine. Then you have to get a vessel, and you have two options, certainly for an inter-array cable. One is that you actually just have when you procure 50 cables, you procure 51 cables and have one as a spare in a factory somewhere. So you might want to completely replace that cable with a as-new cable, and that in many cases can be the quickest way of doing it. Or you can have a qualified repair joint where you get this small section, you hook it from a vessel, you bring it to the surface, you put it on the deck of the vessel, and then you basically cut the bad section out and then splice in a repair joint of say 5 meters or 3 or 4 meters, and then use that as a repair. And the bit that takes the time, my understanding, is basically getting a vessel and getting the parts to do that repair. The actual physical repair might only take a day. It's more getting the vessel and potentially a weather window. You're in the North Sea, it happens in December, you might have to wait a month until you can actually fix something.
Okay, thank you. You all mentioned the cables and getting detailed information from the manufacturer and being able to test the cable. I think most of all, we're on the same page, and we're just using catalogs that are available online, research papers, and so on. If we design our turbine for a specific cable, can we assume, or based on what your comments were, I think that's not true, but can we assume that all the parameters that we obtain from these catalogs are correct? Does the manufacturer actually test every single cable to give us all those correct parameters, or should we buy, I don't know, some kind of samples and test it before going offshore and buying the whole everything that we need? Will or Paul, I think you're the ones that mostly test cables in Catapult. Do you receive those cables for testing just before being purchased in bulk for an offshore wind farm, or does the manufacturer actually send you pieces of cables to test?
Well, I mean, I guess our high voltage laboratory is an accredited test facility, so we help, you know, the cable designers to validate, to accredit their cables so that they can sell them. So more often than not, they will supply the cables that they want accrediting so that they can sell them, and it's very much done on a commercial basis. You know, the test programs agreed, but we do occasionally get cable samples, and we can also quite often, off the back of a commercial test, you know, that there are cable samples that we can use to go a bit further, to go a bit beyond the commercial project, if you like. And that's certainly been quite useful for the dynamic cable test rig, where we've used cable samples that aren't necessarily they haven't necessarily been supplied specifically for a program. It may be offshoots from a commercial test that are quite useful. So, but we do share the challenges that you've mentioned there. That there always seems to be more data that you want, and that either exists but isn't shareable, or it doesn't actually exist, and then sometimes you've got to create it by doing validation.
Okay, yeah. Well, I would like to thank you all for this session. We will close the morning session now, and we'll be back at 2 p.m., 1 p.m. for UK and Portugal. Thank you all.
Okay, thank you.
Thank you.
Bye.
Bye.